Okay, what I'm going to do now is I'd like us to continue on the topic of linear regression a little bit, focusing on, in some sense, two main issues today. One is going to be algorithms for solving linear regression, okay, and the other is a way to formulate linear regression problems so the answers are more robust, okay, and you know. In last time, we showed how you could compute linear regression problems by solving it, reducing it to inverting a matrix and multiplying a bunch of matrices together. And that is in some sense, a good algorithm. Obviously, it's a correct algorithm. But there tend to be a couple of problems with the standard closed form formulation. One is that if you have a large system of equations, a really large system of equations, or many, many points you're trying to fit, the inversion then starts to become very slow. Okay, inversion is an n-cubed algorithm. If n is large, that's bad. Okay. The other issue is that I would say the formulation is kind of brittle. There's kind of this magic linear algebra formula for doing least squares regression, and it works good because it works for that particular variant, but it is harder in some sense to come up with if you have other ideas of optimization you would like to come up with, other kinds of coefficients that you would like to fit. It's harder to necessarily fit it into this nice closed form formulation. And all that together motivates a different way to solve regression problems based on something called gradient descent. That is, let's say, the right way to solve linear regression in practice, as well as many of the other machine learning things we're going to be talking about. So I'd like to go through how that works today. Any questions? Yeah.
You talk about inversion, which is slow for large systems. Are you talking about matrices which are generally dense?
Okay, so there's a lot of linear algebra magic in solving. A lot of people care about inverting matrices or doing linear algebra, and there's an area of numerical analysis that works on doing these algorithms for linear systems. And you're right in saying some algorithms are better for dense for sparse systems than others. And depending upon what we're doing, it may or may not be a sparse system. Bottom line is that for solving these things, gradient descent search is a better way to solve regression in many contexts. Okay, and I guess that's what I would be saying. Is that your question, more or less?
Mine was more on the lines of, is it because considering it's slow only for dense matrices? I'm pretty sure in at least 50 to 60% of cases, it's possible to convert a dense matrix to a sparse.
There is a lot of linear algebra magic that I am not an expert on. Okay, and so the answer of, there's, again, I am culturally a combinatorial algorithms person. Historically, there are numerical algorithms people and combinatorial algorithms people, and the numerical people are a different beast, and they worry very much about these kinds of things. Bottom line is that that gradient descent search is the gradient descent approach is let's say I believe the right approach for solving large systems here. Okay, so that I guess is what I would say. Any questions? Okay, so the key idea here is kind of interesting that we can view regression, before we viewed linear regression, solving regression as being this linear algebra problem. You multiply matrices and what you get are the coefficients of the line you want. Another argument is that we could search for the line coefficients that we want in some kind of a search procedure. And if we think about it, let's think about the very special case of a regression line on just one variable, just for making it simple. We agree that if we were looking for a line of the form, y is some intercept plus slope times x, okay, that what we would like to do is to find the coefficients that minimize the squared error, okay? So if we look at this equation, what is this saying? If our f of x has two coefficients in it, it's a line, we can imagine, look at a formula like this, which is going to be the error function, which is going to sum up over all points in our training test. What is the difference, the sum of the squared differences of the value of the ith target and our ith prediction? Okay? And it should be clear that for any given W1 and W2, this formula gives you the error associated with it. Okay, does everybody kind of get that? I mean, again, you mentally have to substitute the f of x with the, what the full line formulation is. But J here is going to give us what is the sum of squared error. Or really here it's more like kind of the average sum of squared error. Okay, for n training points as a function of those coefficients. Any questions? So an alternate way to try to find these coefficients is to do a search-like thing to try to find what those coefficients are, namely to find the coefficients with the property that they minimize this error function. Any questions about that? Okay. And so the way to think about this, and I want to make sure you think about this right, because if you don't think about it, don't see what's going on here, everything else is just sort of meaningless, is to see that if we have a regression line here, let's say here we're just worrying about slope. Okay, we'll say it is going to go through a one-dimensional thing where it's going to go through the axis, the point, the origin 0, 0. This function here shows us the what is the error as a function of the slope. On this particular example, the slope of 1 looks like it's about what minimizes the error. Does everybody agree that the red line probably fits these points about as well as they can fit? That represents a line of about of slope 1. If we imagine the line rotating, okay, through the origin, so we only have a one parameter fit, it's only going to be the slope that we're looking for, we would expect the error function to look something like this, the middle one. Does everybody kind of see it? That at the point of 1 is where it is minimized. And as we move the slope further and further from the desired slope, the error that we get on these points is going to be greater and greater. Does everybody kind of get that idea? And it's greater and greater in both sides. So what does this mean? In fact, the error function that we are looking for has the property that it is convex. What does convex mean? A function is convex if it has one global minima, global/local minima or maxima. Does everybody kind of get that idea? And what makes that a wonderful thing is that in principle it gives you a reasonably easy way to find it. Our goal here would be, in trying to fit the regression, is given this, try to find what is the slope of the line that will minimize error. Does everybody see that? Now, what this search space does is, in some sense, gives us an idea of how we would guess where the minima is. Suppose we start from an arbitrary point. Let's say we guess that the slope is 0.025. That's about where my cursor is, right? I get an error, and my error here, I could measure once I have that slope what the error is, and my error is up here. My question is now, can I find a way to, to move down, to pick another point that we expect will have less error, okay? And if the function is convex like this, it should be pretty clear which direction we want to go in. If we go up, we go towards a direction of more error. If we go down, we go to a direction of less error, right? If there is only a single global minima and no local minima that we need to worry about, we can't get stuck on the way. Does everybody kind of see that? And we can go bop, 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 down until we get to the bottom of this bowl. And this bowl will tell us what the right parameter was. Any questions? Yeah.
We
No, so what the magic thing that I guess I'm going to trust you to sort of believe is that with that error function, linear regression happens, the error function happens to be convex, which means that it only has one local or global, one global minima and no other local minima, okay? Which means that if we keep walking down, we will eventually find what are the parameters that we want to have happen. Does everybody kind of see it? We are not really searching, we're searching to minimize error, but really what we're looking for is what are the parameters that will minimize error. Okay, any questions about that? This is that same error function on, I believe, the same set of points for the case where we have two parameters, W1 and W2. Here I fixed the intercept value to be 0. And if you look at this, you should be convinced, I guess through the magic of graphics, that in fact this is also a convex thing. This is like a bowl in 2 dimensions. Does everybody see it? And it has the same property that there is one parameter, one point on this bowl that represents the one with the lowest z value, which is the place where there's the lowest error. Does everybody see that? And so, in principle, the same argument should be used to try to find the minimum. What are the two parameters that will minimize this line? We can start at an arbitrary point, and so long as we keep walking in a downward direction, we will get closer and closer to the right point in parameter space that minimizes error. And the regression line that we want is governed by the point in parameter space that minimizes error. Any questions about that? Yeah?
So this behavior is by the definition of linear regression we are getting this behavior, right? Like this is how linear regression is defined.
So the point being is, what should be clear, okay, is that this, in linear regression we are fitting a line. That is what we're doing. That shouldn't be hard. And a line is described by its coefficients, correct? The error of linear regression is given by this, that if we sum up over all n points, what is the sum of squares of the difference between the true y value of the ith point and our calculated or interpolated or predicted value of it, which is given by the regression line. So it should be 100% clear that this is the error function to measure how good or bad a particular fit is, right? And the thing that maybe shouldn't be clear but has to be taken on some level of trust is that this error function happens to have the magic property that it is convex, meaning it only has one global minima and one local, and and that's the only local minima. And once you can prove that that function happens to be convex in all numbers of dimensions, okay, for all possible sets of points, then it should be clear that you can solve any linear regression problem by simply doing this search down. Keep going down until you can't go down anymore. Okay? That's the idea here. Any questions? Yeah? How do we choose the starting point? On some level, the starting point doesn't matter. If you picture a bowl, you have this giant bowl out there, and you have a marble, and you know what a marble is? It's this round stone that rolls around. If I want to get that marble to the bottom of the bowl, what do I have to do? I toss it anywhere in the bowl, okay? And gravity will do its work, and eventually it's going to end up at the lowest part of the bowl, right? So the starting point doesn't really matter in a global sense. Which starting point do I want? If I had to say, what makes one starting point better than another, though? One closer to where it is. So you could imagine that there is going to be some aspect of this that, gee, wouldn't it be great if I could guess a meaningful starting point, okay? But if not, basically it will eventually get there. If I keep moving down, I will eventually get there. Any questions? Okay? So that is how we can use this approach to try to solve regression problems. Any questions? So again, just to summarize what we're taking, this is a notion called, the algorithm that we're going to be talking about is called gradient descent search, okay? Basically, if there's only one possible, if the space is convex, we will find the minimum by just keep walking down. Ideally, the direction we want to walk down on is the direction that is going to get us go down in the steepest possible way. We don't know what our target is, right? But you could imagine a surface where, you know, if this is my thing, I could go down by tilting a little bit down and spiraling around the bowl, or I could go down as steeply as possible. The idea of the steeply as possible is going to be defined by the slope or tangent at the current point where we're at. Okay? Any questions about that? Okay, so let's think a little bit more about how we would try to find what is the right way down. Suppose we were at a point x, y. How would we find the tangent under normal conditions? What is the tangent line? The tangent line is kind of, if you have a surface here, what is the line that just sort of kisses this thing, approximates it the best, that kind of thing, right? Represents its derivative, right? What? Take the derivative at that point. If I were looking at it as a, if it was a one-dimensional thing, on things that I understand, okay? If I had a point x, y, and I wanted to find its derivative, what would I do? I would make x, I would also look at the point x goes to x plus some tiny amount delta. I'd shift it a little bit, right? I'd compute what the y value is at that particular point, right? Slightly shifted. I now have 2 points, okay? That's going to be the tangent line. Those 2 points will define the tangent line. Does that make sense? Okay?
So why would we compute the error function for neighboring point and choose from the least error function value?
So one possibility is, what you're trying to say is that one way we could pick a direction down. You want to say sample a bunch of points around me, figure out which one has the steepest slope down, and then go in that direction. And that seems to me to be one perfectly, reasonable way you could do things, right? If you only had 1 point, though, I claim that if that 1 point, it's either going to, if it's a line, one direction along that line is going to go up and one direction is going to go down. You really need to know which is going to go down and take a step in it. Does everybody kind of agree with that? So based on my knowledge of calculus at this point, I know a way to find a direction that is potentially useful. Does everybody agree? Any questions about that? Now, if you remember, there was something else in calculus that I barely got to. Everyone remember partial derivatives? Okay? Partial derivatives are the real calculus idea for figuring out the tangent, the gradient, the slope that will be the fastest way down. Okay? So if we think about it, the derivative is the slope down, right? If we're in a bunch of different directions, there's many different ways down. In a normal two-dimensional, graph in the plane that we grew up with our simple calculus in, at any point on a line point, there was only one derivative, right? It was only going down. Okay? It should be clear in a higher dimensional space that things get more complicated, right? But it is the case that there is a way to compute the partial derivative, okay, in basically every dimension, okay? And based on that, okay, find what is the single best direction to go in, okay, in order to go down, okay? Any questions about it? So you proposed a way to find a direction that is better than just a random direction going down by trying many points. Even better would be if there was an analytical way to take a look at the points around us, okay, and decide which was the single best way down. Does everybody kind of see that? Okay? And so if you believe that someone has worked out the math for it, these are the partial derivatives. And you can use this to try to find analytically what is the best way down. Any questions about that? Okay. Any questions about that? Now, one thing that I want to say, how much time does it take to compute the partial derivative? This is one thing that's going to drive something we're going to do later. What is the time complexity of computing the partial derivative? Let's say we live in a certain number of dimensions. The number of dimensions is, let's say, k, or d, the number of dimensions. That's the number of parameters in our regression problem. Remember that? This is going to compute the partial derivative in one of those parameters, one of those dimensions, right? How much time does it take to compute the partial derivative or to calculate the partial derivative? Okay.
I think it will not matter much because we will just calculate it for once and put the value for W0 and W1 every time we need to calculate. So
You think you want to calculate it once? Well, there's not really. Look at this formula here. It should be clear that this is linear in the number of example points. Does everybody kind of see it? Just by idea, say, well, yeah, I don't know what this formula means, but I do see it's got a sum as I goes from 1 to n, right? And if this is going to compute for us what the right slope is, the direction to go down to minimize the error, it's clear we've got to evaluate the error at essentially every one of the n points, right? And depending upon where you are, it's not something you can pre-compute once and have forever. It's clear from any given point, depending upon where the points are and where the bottom of the bowl is, I'm going to be trying to figure out the next direction, right? So the good thing about this is that it gives us an analytical way to find what is the right direction to go in, to point, to basically that is the steepest way down the bowl. The bad thing a little bit is that this is going to require linear time to compute what that right direction is, okay, at every step that we walk down it. Does everybody kind of see that idea? Okay, kind of makes sense that it should, because there's an error that we have to compute to figure out whether it's getting better or worse, right? Whether the new point is better or worse, okay? But it should be clear this is expensive. We will be doing this process once with each step that we take down the hill. Does everybody kind of get that idea? If we're going to be trying to figure out what is the best possible direction, okay, we're going to have to do this step n times. We have to do this step a fair number of times, okay, and every time it would be expensive, okay, if we have a large number of points we're fitting. The minima is the coordinates, are the coefficients of our linear regression that minimize error, right? We're going to start at a particular point. We want to find what that point where there is minimum coefficients of minimum error, okay? And the claim is that to figure out which direction is most valuable, we need to look at all the points, okay? And so what we're going to do is to say, okay, I think that this is the best direction, okay?
So why are we looking at all points? Why not just the neighboring points?
Why not look at the neighboring points? Recognize that the points here, this is not the point, a point on this surface is not an input point. A point on this surface is a point in coefficient space. Does everybody see here that the points here are points in example space, x, y space? The points here are in coefficient space. We want to walk in coefficient space, but the value of whether a new direction is good or not depends upon what the points were in, example space, right? So evaluating whether a step here is up or down really involves cycling through all of those examples. Any questions? Okay, any questions about that? Yeah. So you need to find the derivative. Now the derivative, however, right, you need to find the derivative like this for all the parameters. This was the derivative, if I take a look at this, this was the derivative for the jth dimension. You're right that we would have to do this for every single all of the dimensions, which corresponds to one of our coefficients. Okay? So the time complexity for finding the right direction to walk in next is the number of dimensions times n. Okay? We won't multiply, but I think the derivatives here are a derivative, it's a partial derivative, so it's a derivative in one dimension. Okay? So it's basically saying if I'm going to change, what is the derivative, at this particular dimension, this particular parameter. Okay? So we're going to come up with basically a different, as many derivatives as there are dimensions. Okay? And combining them kind of defines the vector that is the direction all the way down. You kind of see that if you could imagine a world where, we decided that in an xy that you had to move 2 units in this direction and 1 unit in this direction, that gives you a vector that says that the right way to walk is out that window, right? And so the partial derivatives give you a way to break it down into, basically dimensional things, okay? And the claim is the right dimension down the bowl, okay, is defined by these partial derivatives. Any questions? How did which two? Okay, this I will say is the magic of presumably the magic of taking partial derivatives. The more interesting question, which you didn't ask, was what does this 2 come from? Okay? And this 2 is just a convention, if you think about it. This is some kind of, this 2 is just used there by convention. This is the error function, okay, right? We want to find a minima in the error function. And whether there is a coefficient here, a 2 here or not, minimize, if we have this 1/2 coefficient times everything, it doesn't change which one of these is minima over all values of W1 and W2. Does everybody kind of see that? If you have a constant multiplier and we're only looking for what is the point that minimizes it, it doesn't matter if I'm measuring my error in wholes or in halves. It's going to be basically the same thing. Okay, so this is apparently just a convention. I don't really know why it's there, but basically it should be clear. It doesn't affect the relative desirability of coefficients. Any questions? Okay, good. And so what is the gradient descent algorithm? Basically what we are going to do is, okay, that for the jth parameter, here the jth parameter, what is it going to be? It's going to be what was the jth parameter minus a change where we find the direction to move according to the, this is basically find the partial derivative, the slope that we need to move, multiply that by alpha, which is a step size. Now that we know what direction we want to move, how far do we actually make that move? Okay? And we update that parameter. And so we're going to update this parameter for every, for all, for J and J, for all the parameters, move to another point, and then keep repeating. Because after we have updated this, we're at a different point in parameter space. Okay? Keep repeating until this doesn't change. Yeah?
And like alpha is tweaked based on like step size to, like it's some measure of like tunability, right?
Right, so alpha is going to be a function that is going to be a tunability function, parameter, about how much do we react. We know what direction is the one that looks like it's going down. How far in that direction should we move? Okay? People call this parameter the learning rate, which I think is a very presumptuous name for it. But it's basically a step size, okay? And if this parameter is large, we will move quickly towards a goal. or we will overstep it. So I guess I've got a slide here to this effect, okay? So if we take a look at something like this, if we are at a point and we use a very, very small step size, we will have the property that we will jump down slowly towards the goal, always making progress, but it might take a long time to get there. Does everybody see that? If we have a very large step size, we could very, very well overshoot the goal. Does everybody kind of see this? If I take too long a step size, if I'm moving in the right direction, ka-chunk, I might move over here, okay? And so there is a little bit of an art here that has to be done to adjust the step sizes. Does everybody kind of get that idea? In principle, when you're far away from the goal, you want the step size to be large. And when you are close to the goal, you'd like to refine your parameters a little bit and make it small. Any question? So there is a certain amount of voodoo in these, gradient descent algorithms that will, about how you adjust these things. Does everybody kind of get that idea? And, one way, actually, just to talk about it, one way that they often do these things is you look to see how fast is the error function going down, okay, as you take a bunch of steps. If you're not happy with the rate at which it's going down, okay, maybe, if it's too slow, maybe you multiply it by 3 and then keep going, okay, or you accept the answer, because if it's not making progress, then maybe you're near the end. Another possibility is that if you see the function jumping around too much, that looks signs that you're overshooting where you are. If it's not always going down, then that means you've overshot it. If it ever goes up, it meant you overshot it, and that's an argument for reducing the step size, perhaps multiplying it by a constant. Any questions?
So this is something that is exposed to the API, like if you have some implementation of linear.
So this should be something that when you look at a linear regression solver or a lot of the learning algorithms will expose the learning rate. Now, in an ideal world, hopefully they have a default, and hopefully you're not going to be playing around with this too much. In an ideal world, a good implementation should have an algorithm to adjust it. But often when people do one of these learning things and they're not happy with the results, they complain about the learning rate, okay, that they didn't set it right or something like that. That is a good way to botch this thing up. Ideally, a library function won't botch it up, but can't make much promises. Any questions? Okay, so let's just go back to the idea here. Okay, any question about the general scheme now? Now I think this should be clear what is going on. It should be clear that we can model our linear regression problem as a search for what the right parameter values are that minimize the error. And that by, because it's convex and because we can figure out which way is going down, we can point ourselves in the right direction and move towards it. Any questions about that? Okay, good. Now, one thing that I mentioned, but I'm gonna gloss over is how do you tell that this function is convex? This requires a certain level of knowledge. I mean, in principle, this is one of these calculus type things. Remember, when you took calculus, how did you know whether or not, if you wanted to know that there was only one maxima or minima, how did you know how to do that? You had this idea that you took the derivative was the slope. If the second derivative was 0, then it meant that you had a maxima or a minima. Remember this? Okay? So in some sense, this should be enough to convince you that the analysis of derivatives is the way that you can, can tell whether or not, whether or not your function is convex or not. And in general, for this business, the people who invent the machine learning algorithms, have analyzed the function to decide whether that is a convex space, and if so, you can use it with confidence that you will get to the solution. Any questions? What? The first, is it the first derivative? Okay, so let's just remember, the first derivative of 0 meant that it meant that it was
Rate of change, that is the initial.
that the rate of change was 0.
If the rate of
Okay?
know whether a point was maxima or minima, we take the second derivative as well, maxima or minima. We put the value of x into that derivative and find the negative or positive. With negative, it was maxima, positive, and it was minima. So we differentiate between maxima or minima with the second derivative.
Right. So we agree that at I think what we are agreeing at is that at the minima, the first derivative will be 0. But whether it's a maxima or a minima is determined by the second derivative. Okay? The level at which I care about this is, yes, I can now see that people who understand calculus better than I do, or analysis better than I do, should be able to figure out whether certain functional forms are convex or not. Okay? And therefore, if they tell me that the thing is convex, then I can believe them and trust gradient descent search. Any questions? Yeah.
For every function, can you actually just calculate its second derivative and see, just to know if it can be, if gradient descent can be applied on it or not? You really have to find whether it's a convex.
So the question of looking at a function and whether or not proving that a functional form like this is convex, again, there's courses there are courses in these kind of things. So it's a more complicated thing, okay? But it should be clear in principle. How would they do it? They're going to take derivatives symbolically, and they're going to argue that they have certain properties to them, okay? And I can believe, this is enough for me to conceive that, yes, somebody who understands these things well enough can look at a functional form and in general say that this is a convex function or not. Yes?
This is for linear functions, right? In the previous lecture, like you did for y equal to 2 under root x, so it will work for that also?
Well, when I did with the previous lecture, that I used nonlinear functions, but that was to generate the points. That wouldn't make any difference. It was still a linear regression on whatever data I was given. If you remember what I was doing last time, I was telling you to build a matrix where basically we knew that yi was supposed to be the linear combination of these variables, right? One of these variables might have been the square root of, if this was x, it might have been the square root of x, right? We're looking for a linear combination of these variables, and where these values came from is none of our business. That doesn't have anything nonlinear to do with it, right? We are looking for a linear combination of these things, okay? And if this thing came from square root x, or this thing came from anything else, doesn't make any difference, right? Normally it came from what? If you have a problem where you have somebody's height, where did somebody's height come from? Came from a ruler, right? Came from a measuring thing, okay? You had no control over what the variables are, what distribution that had, right? So there is no reason why, using a square root here is any different than it's just a function, right? And the important point is that we're making a linear combination of whatever we are given. How we got what we're given is not any of our business. Any question? And that's where we can put the nonlinear stuff in. Yeah.
Also in the last class when we introduced linear regression, we said like when we construct a linear regression, you cannot change the error rate. I mean that was something of that sort we were discussing, and maybe I'm not remembering it properly. Like we said like just shifting the thing will not really help.
Eliminate the error.
No, what?
We had something like that. I don't remember.
Well, what I think. Okay, I'm not sure I'm remembering exactly what we would discuss, what the context here is. It should be clear that if it's an optimal linear regression, if we have the parameters, you shouldn't be able to move any of the coefficients, which is another way of saying that you're at the bottom of the error bowl, right? And taking a step in any direction isn't going to do better.
Right, we were doing that solvers and all, right? Converting from the point to the line, that dimension change thing. And then maybe then the definition is like for the optimal linear regression, not for any linear regression, right? That was something that, maybe I'll go back to this.
Go back to the slides. Okay, any questions? Okay.
We have like multiple linear regression like x1, x2, x3, xn, and
Yeah.
can we still safely presume that this function will be still a convex function?
The answer is yes. It is a bowl, as we have said here. Here's one in 2 dimensions. This is a bowl in two-dimensional bowl. Next thing, it's a 3-dimensional bowl. It's a 4-dimensional bowl. It is still convex. That's the interesting property here. Okay? And so therefore, even though there's a large number of dimensions, there is still only one minima. Okay? And therefore, we can walk down in safety. Okay? Any questions? So that's kind of what's cool. Recognize that what we are doing when we're finding the minima, usually in computer science world, when you find the minima, you're interested in what is the z that minimizes it. Here we are not. We are interested in what are the x and y that minimize z, because x and y are the parameters that we're looking for, right? We're not trying to learn, wow, there is a fit that has an error of only 76. We're trying to figure out what points is it that minimizes the error, okay? And that's where we find the coordinates of the point that is lowest. Any questions? Okay, good. Now, can we apply gradient descent search to the case of surfaces that are not convex? Let's think about this, okay? Can we, let's say that we have a search space that is not convex. Maybe we start out here, okay, we keep going down. Can we apply gradient descent search to that? No. You say no. You say yes. You say yes, but.
It might be one of the local optimals.
The answer is we certainly can apply it. We just lose our guarantee that we get the best possible answer. Does everybody see that? Yeah.
So convex doesn't mean that there is or maybe the definition of minimum is different than what I understand. Does convex mean that you're always going down if you...
Convex is that there is always a direction down that will point to the single global minima. Okay? And in a world of local, where you have a bumpier surface, it is no longer true that there is a single local optima, which means that if you start walking, but you certainly can keep walking in downward directions until you get trapped. Does everybody see that? So what do we know about this point? What would be this point in space? Okay? It would represent the coordinates of a reasonable regression line that isn't necessarily optimal, right? But it's certainly better than anything else we encountered on our tour, right? So we can still do gradient search on, on non-convex surfaces, but we lose the guarantee that we're going to find the best one. And if your space is really, really bumpy, you might get trapped in very, very bad places. Any questions about it? My favorite story is, suppose you were in a cabin in the valley of a ski resort, okay, and you wanted to get to the top of the ski resort to go skiing. If you use if you always go in a direction that will take you up, it might take you to the second floor of the cabin that you're in, and now you're trapped. Does everybody see? There's no place you can get up the mountain anymore, right? Because every other direction leads down. Okay. Any questions about that? Okay, good. And as we said, we went through this, we went through that. Okay, any questions about that? Yeah. When will you get that surface? You will not get that surface solving for, for linear regression problems. But there are other optimization problems for which you will get this surface. So if you think about it, a lot of machine learning problems, in fact, gradient descent search is really used for a wide variety of machine learning problems. Many machine learning problems don't have convex parameter spaces. You guys have heard about deep learning and these neural networks and things like that, and they're not linear and they don't have convex learning thing. But you could still imagine a world where every state of the network is represented by a point in parameter space. You are at a particular point where you set things originally randomly. And now you ask yourself, is there a direction in parameter space that I can walk to that is likely to lower my error? If so, I should adjust the parameters to lower the error, right? and you would keep going until there was no way to adjust it. The good thing is, so long as you keep going down, it's getting better. The bad thing is that once you stop being able to find a local improvement, you don't know for sure that you got the best one. Okay? Any question?
So when the surface is not convex and we are just in one of the minimas or the maximas,
Yeah.
do we just leave it on that, or do we try?
You know, then there's all kinds of games you can play here. One is you could try it again with lots of restarts. Okay? One is you could occasionally take a jump in the wrong direction, right? One is to say that if you've got a problem in a high enough number of dimensions, like in these neural network things, maybe the local optima is pretty good, or good, you know, about as good as you're going to find. Okay? So this recognizes now you're in heuristic world and you can do what you want. It depends how much time are you willing to spend training, and how, you know, how important is it to you to find a better model, right? And this now becomes a cost-benefit thing. But it should be clear that you can do things like a search with multiple restarts, so that you wait till you get to the bottom, then pick another point and see where you end up. It should be clear you can use something like simulated annealing, where you occasionally, if you're trapped in a pit for a while, you take a random jump and see if there's a better way to do it. But now you're in a world of sort of black art rather than a world of guaranteeing the solution. Any questions? Yeah.
How do you know that you have got a local minimum or global minimum?
How do I know if I what?
You are a local minimum, not a global minimum.
How do I know if I have a local minimum or a global minimum? The answer is I don't. You know, just like the guy at the top of his 2nd Avenue cabin, he's looking around, there's no staircase going further on. He might be very happy thinking he's at the top of the mountain. Okay? You don't have any particular way of knowing. On the other hand, if you try another place, you do a walk and you end up at a higher place, now you know that the other one wasn't the highest. Okay? When do you stop? You stop when you get tired. Okay? I mean, if you think about it, there's again, with these things, to a certain extent, there is a cost for doing this. There's a question of how much do you value your solution. You would probably expect that with any kind of a search procedure, there is a law of diminishing returns, right? If I took if I did one random start, I would probably get to this point. If I allow you the best of 2, on average, it would probably be lower. If I allow you the best of 10, it's probably going to be a little bit lower. But does everybody kind of see that the more you look for eventually there's less and less win to be had, okay? And, there's a judgment cost. How much do you want to spend training? Okay? Any questions? Okay? Fair enough. Okay. There are two, any other questions about this, actually, at this point? Let's make sure. There is another variation to this algorithm that turns out to be very, very important in practice, called stochastic gradient descent search. Okay? If we remember about the partial derivative thing, the partial derivative took time linear in the number of examples to figure out the right direction to go to lower yourself another step. Okay? We could imagine, instead of deciding what the right direction is based on all the points, to decide what the direction is based on a relatively few points. Is there any algorithm in computer science that every one of you have studied that tries to do something like this? What? A world where, instead of spending linear time to try to find the best possible, let's say, direction to go, you take a small number of them, okay, and estimate what the right answer is. You say TSP, I don't see that. I don't see A star. Is there any other famous thing that begins with a Q? Quicksort. What do you do in quicksort? Let's think about quicksort. Quicksort, what are we trying to do? Okay, you have a set of arrays. What is the goal that you're trying to find when you're looking for a partition element? What is your dream that element is going to be? The median. We could spend linear time finding the perfect median, right? and say, aha, now I have the minimum, the median, right? What do we instead do? Okay? We either randomly do it, or maybe we will randomly sample a small number of them. Does everybody kind of see that the more, that the more elements you sample, the more likely, if you take the median of the elements you sample, the more likely it is that's a good approximation of the median, right? And likewise, if you're trying to figure out what is a direction that's going to fit these points better, okay, a way to change the current coefficients to make them better, if I sample a couple of the points and find what direction is it that will go and improve it, okay, it should be clear that that will give me an estimate that is faster to compute than going through all of them, right? It's not going to be as accurate, but often, and certainly like in the quicksort case, no one in their right mind would find the median before issuing a step of quicksort, because it just takes too much time, and that a relatively small median on a small sample of things will get close enough on average to be good. So stochastic gradient descent search is something that instead uses only a few examples, possibly even only one example, to try to figure out, for this particular input point, this one, what direction, how would we change the coefficients to make the error less for me? Okay? And it should be clear I can predict, do the direction, what is the right direction for that, would be a constant time operation now instead of linear. The problem is it might be wildly in the wrong direction, because maybe it'll make this guy happy but make everybody else unhappy. Does everybody? What? No, I would say for one training example, for one data point. Okay? No, this represents one point. Let's say we have an original set of parameters, W1, W up to D, right? These are your current parameters. What if now I want to improve these parameters? I will randomly pick one of my points and say, what would be a change in these parameters that would make this point happier? It's got these x values. It's got an associated y value, right? When you take the linear combination of, dot product of that and this, we're going to get a value, an estimate for y. If we take the appropriate derivative, we will find a way to change these things so that the coefficients will change a little bit but be happier for this, make this 1 point happier by making its prediction closer to the target. Okay? It should be clear that this is going to be a faster attempt to go through an iteration than if I had to find the direction that made all the points happier. It should also be clear that I'm often going to be wrong, that what's good for 1 point is not necessarily going to be good for all the points, right? On the other hand, if I pick these things at random and I do enough, it is possible that by lurching towards, I will lurch towards the center faster than I would going through the right direction for each one. Any questions? No. I'm going to, every iteration, what I'm going to do now is, what I did before was take a look at compute the derivative for the best derivative over all endpoints.
Instead of that sigma, we will just take 1 point.
Instead we're going to take sigma just 1 point or 3 points or 16 points chosen at random or arbitrary. Maybe I'll cycle through it, right? And I will pick the direction that makes these points happiest. And assume that if these points are happier, generally speaking, okay, I would, it's generally speaking, it should be in the right direction. Okay? And so you can imagine now that you will lurch towards where you're going quicker than if you took the absolute best step and spent a lot of time for it. Does that kind of make sense?
some points in 10, also there in 20, like.
So the kind of thing you would like to do if you have, let's say you've got 1 million training examples. This is particularly true if you've got a large number of training examples, right? Suppose, let's say, I instead first pick one that's good for the first 10 points, a direction, and move toward, and then take a direction that's good for the next 10 points, and for the next 10 points, and keep going. That would be, after 100,000 iterations, okay, I would have seen every one of these training examples. I would have made 100,000 steps towards the goal in the time that you would have made one step towards the goal, going in the right direction, okay? And the hope that seems reasonable is that if you pick a small but still large enough set of batches to consider, okay, in general, my steps will be in the right direction, okay, or in the right direction often enough that these 100,000 steps, taking 100,000 noisy steps, is better than taking one perfectly defined step. Does everybody kind of see that? So this gives you a way that you can exploit a large number of training examples, yet be fast, okay, make progress relatively quickly towards a goal. Any questions about it?
From a practical point of view, what do we usually use these days?
You know, what do people, so stochastic gradient descent is the thing to use, okay? And so, you know, my students, when they do things, they will tell me, oh, I knocked the batch size down to 1 and it didn't make any difference, it worked just fine, okay? You recognize that it's just like the quicksort example. If I want to find a median, okay, sampling a small number of things, you know, if I sample 1, it's equally likely to be any one of these, right? Does everybody kind of think about it? If I take the minimum of 3, if I sample 3 things at random and take the median of those 3, what do we think is the probability that the distribution on what the median of those 3 are? I'm going to guess that it's probably something like this now, right? If I sampled n over 2 of those things, what's the likelihood, and I took what was the median of these n over 2 that I sampled, what would be the probability, where in the rank space would I expect it to be? Probably something like that, right? Okay? And so the more work I spend sampling, the closer I get to the answer that I want, but the more time it took. And you can, it should be clear that there is a balance to be reached here. Okay? Any questions about that? Okay? And stochastic gradient descent is the way to go, apparently. Okay? Any questions about that? Okay? So this is what your favorite machine learning algorithm probably uses, is an engineered version of this. Any questions? Okay. Let me talk about one last problem for today about linear regression that is kind of an important phenomena, is that there is a problem that we've talked about a little bit in here where you know, it's very, very easy to come up with a feature matrix where there are a large number of variables. We talked about, to make it nonlinear, we could put any one of an infinite number of nonlinear functions we have there. In any data set, there's a large number of features you can build on any example. In principle, if we believe Occam's razor that the simplest explanation is best, we would want our linear regression model to basically come up with what is a good fit that depends upon a relatively small number of variables, rather than a slightly better fit that depends upon a zillion variables. Does everybody kind of see it? You should be able to, who has for any one of a project, how many features do they think they have on any of your data matrices? Does anybody have an idea how many features you've got as on a particular point? What? Could have? How many? Don't know yet.
Could have a lot. 10 maybe.
You say 10, 10's not that much. But I remember, like, when the baby weight group, they had their data set, I think they had 50 dimensions on the weight of what happened to every baby. Did the mother smoke? Did the kid have a twin? Was it a boy or a girl? Is it the first baby? Is it the second baby? Did the mother have diabetes? Okay? You could imagine a model very easily where you collect 50 factors on every single birth that was had, right? And now you want to predict what the birth weight is. If you say, here is the birth weight, the baby weight the baby actually had, and these are all the variables, if you give that to a linear regression thing, what are the coefficient matrix going to look like? What? Well, the coefficient matrix is going to be these W's. It's going to have a coefficient. Each one of these 50, it's got 50 different coefficients, right? It is going to weigh all of those terms together, right? And is it going to, in the process, you know, you can imagine what would happen if, let's say you had 100 babies in 50 dimensions. What's going to happen? It's clearly that it's going to find a way to make use of all these dimensions. Does that kind of make sense? Even if they're not really that important. Even if there were a million, in that case they had like 200,000 babies. But still, if you tried to come up with a linear regression, it should be clear that it's going to find the value of these coefficients that minimizes the sum of squares. All of these things are going to come into play, whether they're really important or not. Does everybody get that idea? So by definition, you run linear regression, you're going to get the coefficients that minimize the sum of squared errors. But all of these, there's no reason why these coefficients are going to be 0. Why do we want a coefficient to be 0? If it's 0, that variable isn't in the model. Does everybody get that idea? So we would like to have a way to convince our regression package that we want to, yes, we'd like to minimize the sum of squares error in our fit. But we'd also like to select the most important variables to do it. Typically what you would expect in a mesh like this is that if you deleted the right 30 variables, the error is not going to change very much, right? But the model will get much more simpler and better understand and probably a lot more robust. Does everybody see that? If you were trying to fit, if you were Newton and you were trying to fit what was the laws of gravitation and you had the choice of square root x, x to the cube root x, fourth root x, okay? You're recognizing that there's not much difference here. The optimal fit would be a spread of all these things, a certain amount of weight on all of them, rather than all the weight on the most important term that really is what you would like to see in the model. Okay? So the principle here that I want you to see is that we would like to be able to convince our regression model to try to pick a simpler model, not have the power to pick a simpler model, not just the one that minimizes error. Any questions about that? Yeah.
So do we combine like decomposition like SVD and then do linear regression, because that is the step that is going to take out?
So one argument here would be maybe what we could do is to take the SVD of the matrix, reduce the dimensionality, and then fit it. That seems like an idea. But what's the consequences of that? First of all, your model is going to now be in terms of SVD parameters and not things that you know about, right? So when you're trying to figure out, maybe you'll have a great model that will predict baby weights, but will you say what's important in that model? Should we be getting, mothers more medical care? Should we be convincing them not to have diabetes, or what is this? Okay? You don't learn that, right? Because there's no variable corresponding to these things anymore. Does everybody kind of get that idea? The SVD kind of rolled a lot of dimensions into one variable that no longer has a name. So that's one problem with this, right? The other problem is that when you're doing these SVDs, you may have rolled all the variables into one, right? So you haven't really reduced all those variables. There's still stuff from a lot of variables there, right? So that's a meaningful thing to do, but not.
You use a lot of other things like PCA maybe or LDA to find the maximum, like which dimension, which column is the maximum.
Any of these data compression methods, dimension and reduction methods will have the same phenomena. that it's going to, that when you do this thing, it's going to construct new features, or the SVDs are new features that are combinations of the old features, right?
We just find out that which are the most relevant to the output variable, like which features. Maybe take the top 10 or top 15 of those variables and just use them for computing the regression model then.
Okay, so one thing you might say is, so recognize that there is a problem here on a feature selection. Okay, you can easily build up a lot of features. You'd like your model to be based on the most important features. You're saying take correlation maybe between these features and the target and take the most important ones. What would be better is if we could convince our regression system to try to avoid using all the variables in quite the way that it would be wildly tempted to do if you don't. So it turns out to explicitly threshold gets us into the world of NP-complete problems, okay? But what turns out to be, just like picking which is the best subset of features is trying over all possible subsets on some level. But there is a way that works sort of like what you want to do that covers, that is a very useful idea. It is something called regularization. And the idea here is, what if we add make our error function a little bit more complicated to account for the cost of having a lot of variable coefficients that are bad. Okay? So there are a couple of different issues with coefficients. One terrible model, okay, so there are a couple of different issues here, but let's look at what this particular error function is. This part over here was the exact error function we looked at before. Does everybody see that? This part is the summing up over each point, what's the difference between the prediction and the real value. This here is a second term that is a sum over all the parameters, the coefficients that we use. It's the sum of the square of the parameters. If we want to minimize the sum of this incomplete function, what's going to happen? Minimizing the function here involves setting the parameters so that we get very little error on the testing. This part of the function is going to encourage us to keep our regression coefficient small. Does everybody kind of get that idea? If it's the sum of squares of the regression coefficients, obviously this is going to be saying that we want to minimize the absolute magnitudes of those coefficients. We don't want those coefficients to get very big or very, very small. Yeah?
Isn't the problem the number of coefficients, not the size?
So there are two different problems here. You're 100% right. There are two different problems. One is a problem of the size, and one is the problem of the number of them. I had been talking about the number of them, and you're right, when you look at this thing, this is going to be minimizing the sum of squares of the coefficients. That's going to be minimizing size. Why does that matter? I have seen from when I built regression models on two variables, occasionally you will get a fit of the form, huge number minus huge number times x. Okay? And this is an ugly thing. Does everybody kind of get that idea? Okay, if I said the best fitting line for weight and height is you multiply the weight by 17 billion and subtract from that 393 billion. Okay, does everybody agree that would be a silly model, right? You want a simple model, that doesn't seem like that should be right, right? So for these, that's an argument that you want to also minimize the absolute magnitudes of these things. If you've seen what came out of a fit, you would realize this is a real problem. Okay? So this here, by summing up the squares, is going to minimize the size of the coefficients, right? And this encourages you to tamp them down. Now, of course, the best way to tamp them down is to send them to 0, right? Then you don't pay any penalty for this. Okay?
Does it mean that these 1700 billion and whatever numbers that we were discussing, they were just multiplicative factors of what otherwise could have
Well, they were multiplicative factors, but do you see what happens is, let's say I wanted to convert a number. Let's say I wanted to get a number of 100. One way I could get 100 is 10 plus 5 times, what was it, 18? No, 5 times, I think it's 18. Does everybody see that? Another way I could get 100 would be, a billion minus, a billion divided by 18 times 18. Does everybody see that? So you could easily see where, if you had this question, if you had the choice of looking at two models, which one of these models do we like better? Okay? In practice, this is a more interesting set of models. We would like to encourage such things. Okay? And it should be clear. What should be clear? It should be clear that by giving this penalty, we're going to encourage coefficients being small. It should be clear that that doesn't actually reward us by itself to setting it to 0. Okay? But it turns out that there are different ways of normalizing these things. Okay? And, depending upon whether you take the sum of squares or the sum of the absolute values, there are different forms of regularization. Okay? And I believe it is when you take the L1, the sum of the sum of absolute values, that will then try to minimize the number of coefficients. Okay, that will reward you for driving to 0. The squared one keeps the parameters small. It should be clear that playing with this error function, be it sum of squares or the sum of the absolute values, okay, gives us a way to encourage the system to find a minima that looks better to us. Does everybody agree with that? That should be clear. Okay? And this turns out to be very, very important for avoiding bad models, for simplifying the complexity of it. If we set a large value of lambda, that's a coefficient, that means that we're going to view this as being more, larger we set the parameter lambda, the more we view what we do with the coefficients, okay, simplifying the coefficients as important. The smaller we make lambda, the more we make the error minimizing being more important, okay? And bottom line, this is a thing one should play with to try to build a good model. In general, we want our models to be simple, okay, and regularization is a very important thing to avoid overfitting, okay, by encouraging us to simple models. Any questions? Okay.
I don't get this idea. Why are we doing this? If we have fancy numbers for coefficients, it's still the same complexity, right? It will still be a linear model, linear complexity, or all of the different.
No, it's a linear complexity, but recognize if I wanted to predict if I wanted a robust way to predict your GPA, okay, the model I would like it to look like is it's going to be some constant times your high school GPA plus some constant times your test scores, right? But if I also know other things about you and your thing, like how old you are and your height and weight and stuff like that, if I had height and weight in my training set, does everybody agree that if I had somebody's data set where I had their high school GPA, their test scores, their height, and their weight, and I asked you to build a regression model to predict what your GPA was at Stony Brook, there is no question that model is going to find a way to use the height and weight to better fit the training examples I have. Oh, we have this very smart guy who's also pretty portly. Let's give those pounds a couple more points, right? That's good, okay? And if that was true, this would create a model that would have less error. It should be clear that if I delete these variables, the training error can only get higher because I have less freedom to fit the points. But in practice, what we would like to see is the coefficients here and here are probably going to be much larger than the coefficients here and here, because these should be less important variables, right?
Suppose we are predicting the GDP of a country, suppose it will have a very high y-intercept, maybe in billions or so, but you won't like that thing because it is having very high value, so we'll put...
Okay, so if the y-intercept is high, then maybe I should have subtracted that off from all the points before I started. Okay? Again, the principle that should be clear is that in general, a model like this looks better than a model like this. Okay? If the fit for this model is slightly worse than a model like this, I would rather have that model. And if a model on 2 variables is slightly worse than a model on 4 variables, I want to have it. Regression is going to be obsessed with trying to minimize error before, unless we use regularization. And it's going to seek to use every parameter as best it can. By adding a penalty for having a lot of parameters or for having large coefficients, okay, this is going to, the optimization will have some way to try to fit the models we want. Any questions about that? Yeah. Yes.
So the function is a combination of many features, and that can or cannot be linear, because we can add any feature which could be square root x or
Right.
the power of x.
Right.
Then why is it called linear?
It's linear because the function that we are constructing, our prediction is y is equal to the sum of the ith coefficient times the x to ith variable. Right? So suppose we have a function like 3x plus, 2x squared. Is this a linear function? You say no. But if I have and you're right, it's quadratic, right? But if I had a variable, a data set that gave me x and x squared, this could be found by linear regression. Does everybody see it? And so it's linear in terms of the variables you give it. If you give it variables that correspond to nonlinear terms, it is finding the best linear sum of, variables in these nonlinear terms. Okay, that's the mystery here. Any questions? Okay, think about it, but instead of thinking about it, right now we have a speaker going on, starting in computer science, on a data scientist, a very good one, who's talking about evaluation in social media. I encourage everybody to come, okay? Please, if you can come, I would like you to come to the talk. 120 computer science right